Traditional food processing has a single absolute biological objective: achieve microbial safety. For over a century, the primary mechanism has been prolonged heat exposure, designed to lyse or rupture pathogenic cells. Look at this legacy hardware. Systems like these rely entirely on holding liquids at high temperatures for extended periods to guarantee that no harmful microbes survive. But this brute force application of heat creates a physical paradox. The exact thermal energy required to denature a pathogen cell wall indiscriminately degrades heat-sensitive bioactive compounds like vitamins and antioxidants, while permanently altering the food's rheology and texture. Because heat moves as a gradient from the outside in, the periphery of a product is severely overprocessed. By the time the core reaches the target kill temperature, the outer layers have already undergone severe lipid oxidation and nutrient loss. In traditional systems, you cannot separate safety from destruction. The absolute cost of an entirely sterile product is the irreversible structural degradation of the food matrix itself. To bypass this thermal damage, food engineering has shifted toward non-thermal processing. Instead of heat, these systems use mechanical, electrical, or chemical energy to dismantle pathogens. These interventions achieve specific microbial log reductions strictly at ambient temperatures, typically operating between 25 and 65 degrees Celsius. However, eliminating heat introduces a severe complication. No single non-thermal technology can universally replace thermal processing across all food types. The industrial viability of any non-thermal intervention is strictly bound by the feasible architecture, the matrix, of the food being processed. Engineers are no longer fighting temperature profiles. Instead, they are battling the electrical conductivity, density, and chemical composition of the food matrix itself. The most commercially established method is high-pressure processing, or HPP. This is a mechanical intervention that uses water as a transmission medium to deliver physical force. A sealed chamber applies 200 to 700 megapascals of isotropic hydrostatic pressure. This uniform force avoids uneven thermal gradients. At the cellular level, this extreme force collapses non-covalent structures. The bacterial membrane ruptures, neutralizing pathogens while leaving smaller flavor molecules intact. While HPP effectively neutralizes vegetative bacteria, both gram-negative and gram-positive, it faces strict biological limits. The pressure cannot fully inactivate highly protective bacterial spores. Furthermore, endogenous enzymes like polyphenol oxidase are highly pressure-resistant and often survive the treatment. This means HPP guarantees safety against active cells, but surviving enzymes risk degrading the product's flavor over time. Add in the requirement that HPP must be run as a batch process, and its physical architecture severely bottlenecks continuous industrial throughput. For continuous, flowable systems, engineers utilize pulsed electric field, or PEF, technology. Rather than mechanical force, PEF fires an electrical pulse ranging from 25 to 85 kilovolts per centimeter through the product, lasting only milliseconds. This triggers electroporation. The intense electrical field forces the microbial lipid bilayer to separate, ripping physical pores directly into the cell membrane. Secondary agents like hydrogen peroxide then flood through these pores, rapidly oxidizing bacterial lipids and immediately inactivating the cell's metabolic enzymes. The limitation here is strictly electrical. PEF efficacy depends entirely on the uniform electrical conductivity of the food matrix. If a solid or highly heterogeneous food is processed, internal variations like air pockets or varying fat densities distort the electric field. This uneven distribution creates isolated cold spots where pathogens easily survive. PEF achieves consistent microbial inactivation for uniform liquids, but the moment structural heterogeneity is introduced, the electrical field is rendered practically useless. Another mechanical intervention is ultrasound, which operates at high frequencies between 20 and 100 kilohertz. Passing these sound waves through a liquid medium generates cavitation. Microbubbles form, followed by their rapid, violent collapse, creating chaotic micromixing. The collapse of these microscopic cavities generates massive localized energy spikes and extreme shear forces that physically shred adjacent bacterial cell walls. The critical matrix limitation here is spatial. High-frequency sound waves suffer from extremely poor penetration depth when applied to dense or bulk matrices. Because the mechanical energy dissipates so rapidly upon contact with mass, ultrasound is restricted almost entirely to surface decontamination, or processing very thin films of liquid. Cold plasma represents a chemical intervention. It utilizes the fourth state of matter, created by ionizing gases like argon or nitrogen at near ambient temperatures. This ionization process generates highly reactive oxygen and nitrogen species, bombarding the target surface with free radicals and electrons. These reactive species are incredibly effective. They chemically degrade complex agricultural pesticide residues and efficiently destroy the DNA structures of surface-level bacterial biofilms. However, the reactivity cannot be perfectly isolated. These same species trigger rapid, unintended oxidation of the lipids and proteins within the food matrix itself. While cold plasma serves as an exceptional surface decontaminant, its highly oxidative nature damages the core quality, creating rancid off-flavors in fat-rich foods. Examining the empirical performance data of these systems reveals exactly why no single technology is sufficient on its own. This chart maps the systems against microbial reduction, energy, and nutrient impact. HPP offers high log reductions but demands massive energy. PEF delivers high reduction with low energy, but is restricted to liquids. Cold plasma uses minimal power but heavily degrades nutrients. Because of these matrix trade-offs, combined with the persistence of bacterial spores and resilient endogenous enzymes, relying on any single non-thermal intervention leaves the food matrix vulnerable. To overcome these isolated technological vulnerabilities, industrial processing is evolving toward a multi-herd architecture. This approach systematically combines a sublethal, non-thermal physical disruption with a secondary, mild electromagnetic intervention. The initial non-thermal phase, like a rapid electrical pulse, strips away the easy biological targets by completely destroying the weaker vegetative cells. This leaves only the highly resilient spores, which can then be safely neutralized using a much lower, less destructive thermal or ultraviolet energy threshold. By splitting the workload, this synergy drastically reduces overall processing time and energy consumption compared to forcing a single method to operate at maximum intensity. Modern food engineering optimizes microbial kill rates and nutritional density by designing these specific engineered synergies that preserve the delicate food matrix in its absolute highest quality state.